Thanks for the introduction. Well, let me start by giving the thanks that I'm supposed to be giving. So thanks to the organizers also of the workshop. Speak here. And so far, I'm really impressed by the organization, I have to say. It's a really nice workshop so far, and I hope to be able to talk to many of you still in the rest of the week. Also, thanks to my supervisor, Marcello Seri, who is in the audience, who also has helped me a great deal in this research. So he's also giving a talk tomorrow, so I have the pleasure of doing the introduction with half an hour less time than he has. I'm sure you will be grateful to me as well. So let me get started. I will explain first what sub-Riemannian means to just everyone in the audience who is not an expert. I know some people here are, but so I hope I don't insult you. So let me start with a very simple geometric setting. Let's say we are in R3, and I give you two, let's say, smooth vector fields on R3. So at each point, they define a subspace, the tangent bundle, which I call the distribution, which is not the distribution that we saw in the previous talk, and also not the distribution of generalized function, but distribution as in subspace of the tangent space. And we ask a question. So let's suppose we are in a system which has constraints, and we're only allowed to move at each point in the direction generated by these two vector fields. So our curves gamma that we call horizontal, they satisfy an ODE where the components must at every point be in the distribution. U and V are control functions that we are allowed to choose. And the question is it possible to go from any point to any other point in such a way? So the answer is, well, it depends. It depends on what we choose as these vector fields. So on the left picture, you see space is nicely, in the technical lingo, foliated by integral submanifolds, but it basically means that there's a stack of papers on top of each other where you can never move from one piece of paper to another piece of paper by staying tangent because, well, you're stuck. And here in the setting on the right, you can see that the planes are turning enough to allow for some movement between the different layers. Well, the secret is that there are not any layers. So clearly it depends a little on the vector fields. For example, well, the simplest possible case is when you take 2 and 3 coordinate vector fields, you will clearly be stuck in Z. You can never move up or down. So how do we know? Well, I give you an example. This is probably the most famous one. This is called the Heisenberg group on R3. It's called a group because these vector fields are left invariant with respect to the Heisenberg Lie algebra, Lie group on R3. And these two vector fields, they form a representation for the Heisenberg Lie algebra in the sense that they are commutator. It's d and dz, which is easy to calculate, which means that at every point, if I look at x, y, and the commutator of x and y, they span the full tangent space. And this is a sufficient condition for being able to go everywhere. Why is this? Why the commutator is important? Well, I have to give the compulsory example of parallel parking. So if you do the commutator of x and y, you do x, then y, then minus x, and then minus y. So which corresponds in parallel parking to going forward, turning the wheels, going backwards, and turning the wheels backwards. So you cannot immediately shove the car from left to right into the parking spot. Would be nice if we could do that. And so I show this picture at all of my talks because it's a compulsory example, but because we're in the UK, I had to go through the I didn't manage to mirror the numbers, but so clearly the commutator is important. So in this case, when we have the commutator, we can reach everywhere. So let me get to what a sub-Riemannian manifold is. So it's a connected manifold M together with some collection of vector fields x1 up to xm. M is unrelated to the dimension. The manifold, it can be the same, less, or more. And the important thing is that they generate brackets, which means that at every point, if I continue to take Lie brackets of these vector fields, eventually I get the whole tangent bundle. And well, maybe you have to take more iterated commutators, so you get more complicated motions. It's more difficult, but you can eventually reach everywhere. I also include the data of a smooth metric on each distribution, which allows me to measure, well, it allows me to do geometry, to measure angles, lengths, whatever. And I also, for this talk, this is not always the case, but I include the data of a smooth volume form on M. If you really want non-orientable manifolds, you can replace this by density. And this choice is free. There's no relation to the vector fields x1 to xm because there's no canonical choice. So this is actually related to important problems in sub-Riemannian geometry. So for now, I just choose one and we work with it. And the curve is horizontal if there's a control function. Well, if it's completely tangent to all the subspaces at every point. And because of bracket generating assumption, you can reach from any point to any other point. So from this structure, you induce the structure of a metric space on M by taking the infimum over all horizontal curves connecting the 2 points. And this topology that this metric induces is the same as the original topology. Okay, so this is a good structure. You can ask lots of questions regarding the classical motion of particles, but we are at a spectral theory conference, so I want more PDE related problems on sub-Riemannian spaces in order to study kind of the wave motion or the heat motion on these types of spaces. The motivation for studying these manifolds as well. Sub-Riemannian geometry is the geometry of control problems, of constrained motion. And as I've been told by engineers, you know, in real life, all problems are constrained. There's no free lunch. So this is a geometry that really comes up. There's lots of applications to robotics, to human vision, to quantum systems. They're quite wide. I can give you references if you're interested. But so also the motivation for studying really the spectral properties are that we want to understand the geometry of these spaces, and the geometry tends to be related to properties of the spectra. So maybe from the spectra we can understand something more about the spaces. Okay, so to do that, I want to see something about heat flow in sub-Riemannian spaces. This is how it works classically. So heat tends to flow from hot to cold in the direction of the gradient, so in the steepest descent. And there's a conservation law, meaning that the change of heat in a certain region should be equal to the amount of heat that flows out of that region, but shouldn't just get lost somewhere. So if I want to define this in a sub-Riemannian setting, what do I actually need to tell you? Well, I need to tell you what this gradient is, because it should be in a horizontal direction. It's not just the sum of derivatives. I should define this n that appears, because that should also be horizontal, because you see it's being dot producted with f, so I should be able to calculate the inner product of n. And I should tell you what the volume form and the surface measure are. Well, the volume form, I gave it to you. It's just arbitrary. And the surface measure, once I give you the normal, it will be the contraction of the given volume form with the normal. So that's it's not the biggest problem. So let me define these first two items for you. So the horizontal gradient is a relatively simple generalization Riemannian gradient. Namely, it's defined as the unique horizontal vector field such that G of the horizontal gradient with any horizontal vector field is equal to the directional derivative of U in that direction. So it's abstract definition. You can prove that it's characterized by just xi acting on U times xi, where xi are the frame of the horizontal vector fields. So, I mean, in the Riemannian cases, it's easy to prove because you just take xi to be an orthonormal frame. but especially if these xi's, you know, it can be that that the dimension of your distribution changes point to point. This is not something that we're assuming, but using some linear algebra, you can still prove that this holds. In fact, this took me some time to do because it is written in 2 different places, and in both places it's an exercise. So I thought, well, I have a proof written, and it was going to be part of the paper, but it was getting long, so I removed it. Maybe it will be in my thesis, but depending on circumstances. So that's the horizontal gradient. The horizontal normal is, well, I told you it should be in the distribution, and there are 2 types of points to worry about here. So a characteristic point is a point where the distribution is completely inside of the tangent space to the domain. So this is not a characteristic point. A characteristic point in, well, in this 2-dimensional drawing, it would be when the distribution is actually parallel to its tangent plane, and then we're kind of screwed. So these characteristic points are quite bad. But then what we do is we set the normal just to 0. And sometimes you can ignore problems that come from characteristic points and sometimes not. But okay, we have to do something. And in the other case, you know, when the distribution is not completely inside of this n-1 dimensional subspace, you know that together they have to span the tangent space. So you know that you will be able to find some vector in the distribution that's orthogonal to this subspace, and we just pick one plus some orientation. So it's up to minus signs. This is uniquely defined. Okay, so that defines all the ingredients in that formula for the heat flow that I showed you on the previous slide. So what we can now do is, well, I state a very short lemma. So here's the surface measure, so the contraction of horizontal normal with the volume form. And something that you can prove in a few lines is that if you have F dot NH, that this is equal to just contracting the flux. So also in the Riemannian case, this is standard lemma, and in the sub-Riemannian case, prove it by first proving it for characteristic points and then for non-characteristic points. For characteristic points, it turns out that lots of things will be 0. For non-characteristic points, it's the usual proof. So this is in my paper if you want to read it. This did make the final cut. So if you plug that in, so remember we had the integral over the boundary of F dot and H integrated over the volume form. So this is now the insertion of the flux into volume form. And by Stokes' theorem, I can move this partial d here to get the Lie derivative. And this should be equal to divergence vector field. So the conclusion is that heat flow outwards by pulling this partial derivative inwards has to be equal to this integral, which has to be equal to, well, the one here. So what we should study is ut equals divergence of gradient of u, but now divergence of horizontal gradient. So I mean, it's the same usual derivation of the heat equation, but so this is the operator that we should study, divergence of gradient. Okay. We want to study some properties of the spectrum of this operator on some domain omega inside of a sub-Riemannian manifold. And we have to put boundary conditions. So I will do either Dirichlet, mixed, or Neumann is what I studied here. For personal reasons, I was mostly interested in Neumann boundary conditions. But I have to start with Dirichlet because it's simpler. So theorem is as follows. This is the generalization of the Cheeger, classical Cheeger inequality. So we take a bounded domain with piecewise smooth boundary. I don't want to worry too much about smoothness of the boundary. It needs to be smooth enough so that you can apply Stokes' theorem to it, basically. Then the first Dirichlet eigenvalue is greater than or equal to 1/4 the Cheeger constant squared, where the Cheeger constant is the infimum over A that are well contained inside of the domain of the surface over the volume. Okay, So I will show you a brief sketch of the proof, and a lot of the work has been done for me already in previous talks, especially in the last one, so I can be very grateful to the previous speaker. So I take an eigenfunction, u, corresponding to this first Dirichlet eigenfunction. And the magic is to study this integral, the integral of the horizontal gradient of u squared. By the chain rule, that's equal to this quantity, and by Cauchy-Schwarz, it's bounded by this norm. And since we have the variational characterization of the first eigenvalue, this norm of the horizontal gradient I can replace by the eigenvalue times the norm squared, or just once the norm actually. So this is 1/2. And if I look again at this quantity, now I want to bound it from the other direction. So this is really the magic step. I will explain where it comes from on the next slide. So this, at the same time, this is greater than the Dirichlet Cheeger constant times the norm squared of u. So if you just concatenate everything that's written on the slide, you achieve the Cheeger inequality, modulo the fact that I didn't tell you how to do this, which I will do now. And it relies on the co-area formula, which was mentioned in the previous talk, but just for completeness, let me explain where it comes from. We have also in the sub-Riemannian case, due to this paper, have co-area formula. And the idea behind it is that, well, imagine that omega is this cat, and you want to integrate some visible function over the cat. Well, the idea is the stripes are the level lines of f. You first integrate over each level line and then over all the lines. This is part of my hobby or life goal to explain mathematics using pictures. So if you're at a birthday party, which really is the worst possible setting to be in, and someone finds out you do mathematics, I always explain my research also using cats. So if you're interested, then I can try to do that. And also, if you have other mathematically relevant cat pictures, I have a folder on my laptop where I save them. So if you have any other ones, you're free to email them to me because I collect them. Okay, so we have this formula.
Excuse me, can you remind me what is sigma?
Sigma is the measure on the surface. So it's the
measure on the surface,
no,
on the level set.
On the level sets, yes. So they are for non.
The usual.
It's the contraction of the horizontal normal with the chosen
omega.
Yes.
Horizontal. Okay.
Yeah. So, by the way, if you look at this paper, it's all geometric measure theory. So it doesn't look anything like this, but it works. So now, this integral that we had on the previous slide, I can rewrite using co-area formula. And now this integral here is exactly the surface measure of the level set u squared equals t. And because the Cheeger constant is the infimum, I can replace this by just the volume of what it's the boundary of. And this last integral here is equal to the norm of u squared by some funny thing called the layer cake formula, which I think is amusing. So that's the proof of co-area formula in the Dirichlet case. Very nice. What I can quickly say is that there is a way to bound the Cheeger constant, because notoriously it's difficult to compute. And this theorem here is something that is known as the Max-Floeming-Cut theorem in the Euclidean case. And it's a way to produce lower bound for the Cheeger constant, hence a lower bound for lambda1. And this is not in my opinion, not a very well-known result. In fact, I didn't know about it until I gave this talk, and Daniel Grieser, who did this proof, was in the audience and told me about it. So the proof is not so complicated. So there's 3 steps. And the only complicated one is the first step, because this is the divergence theorem, and this is a triviality because the divergence of this vector field is chosen to be bigger than h pointwise.
What is this? Just horizontal vector field? V is any horizontal?
Yeah, if I give you a horizontal vector field which has norm less than 1 and pointwise large divergence, then that gives you this lower bound. So you have to find V, but it's easier than lower bounding the Cheeger constant, because you can't take just an arbitrary set and then draw a conclusion. You have to really go for all sets. So this is more computable. Okay. So the only difficulty is this first inequality, and it's proven this, relatively speaking, the same way as the lemma that I showed you when we were deriving the sub-Laplacian. You split it from characteristic points and non-characteristic points. In view of the time, I will not explain how it's done, but maybe if you want, we can go over it afterwards. So we have a computable way to lower bound this first Dirichlet eigenvalue. Okay. So now I move to mixed boundary conditions. And maybe it's not a surprise, but you have exactly the same case for mixed boundary conditions. The only difference is how the Cheeger constant is defined. So you have to have an A test set whose boundary doesn't meet gamma. Gamma is here the part where Dirichlet boundary conditions are enforced. And the reason that we need this is how the level sets of the first mixed eigenfunction look. So they cannot touch this part of the boundary, but they can touch this part. And then if you take the infimum over all such sets and you run exactly the argument that I was showing in the previous slide, you will achieve this bound on λ1 mixed. So, okay, who cares? Well, I care a little bit about this because I have a reason for caring about Neumann boundary conditions. So we also have a Cheeger inequality in the Neumann case. And it's almost the same, but it's different. So now I have a bounded domain with piecewise smooth boundaries, smooth enough to apply the theorem of Stokes. And I have to put an extra assumption, namely I want to have a unique continuation of eigenfunctions, which means that if an eigenfunction of the problem vanishes on an open set, then it vanishes everywhere, which you have for free in the Euclidean case, and which you have if the manifold, the vector fields, and the volume form are all real analytic. But you have to assume this. I don't like that, but we need it. Then now we have an inequality on the second Neumann eigenfunction because the first one is always 0. And it's still greater than 1/4 times the Neumann-Cheeger constant. And I explain now what the Neumann-Cheeger constant is. Neumann-Cheeger constant is the infimum over the area of some hypersurface that cuts domain into two parts, omega1 and omega2, divided by the ratio, but divided by the minimum of the volume of omega1 and omega2. And where this comes from is we have to look at the nodal domains of a second Neumann eigenfunction. Okay, so I take an eigenfunction corresponding to λ2 by Courant's theorem, which holds for sub-Laplacians, but this has to be proved. It has exactly 2 nodal domains because it has less than 2 by Courant's theorem and more than 2 because it has to vanish somewhere to be orthogonal to a constant. So roughly speaking, we have a picture that looks like this. Here's the nodal line. Here's omega plus. And now if I take the restriction of the Neumann eigenfunction to this, it satisfies a mixed problem as we saw in the talk yesterday. So this U restricted to the nodal domain is an eigenfunction for the mixed problem. So by the mixed Cheeger inequality, I can say that λ2 Neumann is in fact the first eigenvalue of a mixed problem, which is greater than 1/4 times the mixed Cheeger constant, which is greater than the Neumann Cheeger. But this is a little argument that you need to think about for a few minutes, but it's not complicated. And that proves the Cheeger inequality also in the Neumann case with some technical details. So the technical details are the fact that Courant's theorem is meant to hold and the fact that this restriction should be an eigenfunction. So let me comment a bit on that. So this nodal domain theorem holds in the Laplacian case, and this is for Dirichlet boundary conditions due to this paper here by Eswarathasan and Letruy of last year. It's quite recent actually. There have been some recent interest in nodal sets for sub-Laplacians. And this proof that they give here holds pretty much 1-for-1 for also Neumann and mixed, so that's good. And the second part is this restriction theorem, namely if you have U, which is in this space, which is S1, which is kind of H1, but only you have to have the derivatives in xi that are in L2, not all the possible derivatives. And that vanish where they're supposed to vanish. And I take a nodal domain, then the restriction of this function to the nodal domain is in the correct Sobolev space of the restriction. So this gamma I is the part of the nodal domain omega I where this restriction is supposed to vanish, namely on the nodal lines and on the Dirichlet part of the boundary. Right, that's what this gamma I is here. I don't write the precise definition, but if we had this nodal domain here, the gamma I is this red part together with the orange part that is the Dirichlet part of the boundary. Okay, so this is also a slight technicality. And initially to prove this, because this is really crucial for Courant's theorem, we had to assume that the boundary had no characteristic points so that we can use a result that says that eigenfunctions are really smooth up to the boundary. That's nice, but this result by Frank Helfer of the current year is avoiding that completely. So that's a really nice thing that we have, because very often characteristic points can screw you up. Okay, let me finish with some final remarks. So the issue of unique continuation is here probably analyticity of the entire structure is not the minimal assumption that you can put to have analytic to have the unique continuation property, but maybe this exists under weaker conditions. I currently don't know. Then another point is the Max-Flo-Min-Cut style result for Neumann boundary conditions. So you can do something that I showed you earlier, but there's some technicalities, namely that you need to, when you integrate over sigma, the integral over boundary of A in the Dirichlet case, but when you do integral over sigma, you have to close it up with the part of the boundary of omega. And because stuff is not vanishing there, you need to put an additional assumption that is not really nice. But it does work if you have an omega that doesn't have a boundary. Like if you put this on a manifold that doesn't have boundary like T2, the argument that I showed you earlier works. Otherwise, I don't necessarily know a computable way for the Neumann constant. So if you know, then feel free. And the last point that I will make is an advertisement for Marcello's talk of tomorrow. So one thing that I focused on here is that we are dealing with structures, sub-Riemannian structures that can change rank. And this is very typically a bad property. For example, the two vector fields that you have here, the vector field y vanishes when x equals 0. So the rank of the distribution changes. Normally this is bad. We can treat this with our method with no problem if we put the volume form that is smooth. So if you put omega is dx wedge dy, you can treat this in my framework. But that is maybe not the most natural thing to do. The most natural thing to do may be to take these two vector fields and declare them to be an orthonormal basis. And the volume form that you get then is 1 over x times dx wedge dy, which is not smooth. And there you get some very interesting phenomena that I'm also really interested in studying eigenvalue bounds for, but that Marcello will tell you about tomorrow, what we know in that case. So with that said, thank you for your attention.